Section 9.9 is called impedance ratio. And this is just amazing, interesting ability of this transformer has to actually transform not only voltage and current that we normally think of when we talk about a transformer, but a transformer can also transform an impedance from one value to another. Okay, now if you think about that for a second, you think in terms of Ohm's law, it makes sense. You think about relationships and, current, voltage divided by current is impedance, right? And so I can transform voltage, I can transform impedance. So I can transform voltage, I can transform current. It sort of starts to make this sense, and there's some logic to the idea that if impedance is defined in terms of voltage and current, I can also transform it. And section 9.9 is about that. And let's go through this. I think it's really interesting. So here's figure 912, and now we're using this new representation of our transformer. It's just this. It's this rectangle. It's got the transformation ratio here, the N1 over N2. We know the primary side is connected to the source, and the load side is the secondary. And so we're using this symbol. And of course, we've got our polarity marks here and the current direction shown as well. So it says, what happens in an ideal transformer, and I guess that's indicated by that letter T, is connected between a source and a load Z. And we've got the transformation ratio written there. There's this thing that occurs, and I guess the best way to sort of begin with this idea is to go through mathematically how we get here at this idea. Okay, so without saying what that idea is, let's walk through this first. Okay, we know this E1 over E2 is equal to this turns ratio. That goes back to this equation, right? And N1 over N2, and we're just taking that aside and using this part of it. We also know in terms of, I think it was equation 9.7, that this relationship exists in terms of the inverse relationship with the current. All right, so as I look at this slide here, and I look at what this voltage source sees, and when we say see, what is it working against, so to speak, and the impedance that it's dealing with is going to be the voltage, right, divided by the current right here. And so we're representing that here. And then on the secondary side of this, this impedance could be defined, right, again as E voltage divided by the current here, right? And so that's what I'm showing on this side. And hopefully this will reappear. There it is. This is lagging internet day. Okay, so if that is the case, then I can do some things here, and it's just really simple math of replacing defined quantities here. But if the source sees this impedance that we're calling Z sub X, and it's defined as E1 over I1, well, as I go back to this, if I solved this for E1, it would be E2 times A, right? And so that's all I did right here. I replaced the E1 with that. And then I sort of did a similar thing over here with I1. I1 would be, if I solve this for I1, it would be this, or another way to write that would be I2 over A. Okay, so that's where that comes from. That's where that transformation comes from. Then it's just a simple matter, you know, it's a fraction over a fraction, you know, invert and multiply. So I end up with A times A, or A squared. The E squared remains and the I squared remains. Not, well, uh-oh, I've got that written wrong. That's not a squared term, is it? It's just a subterm here. But the transformation ratio is squared times E2 over I2. Now, if I already know E2 divided by I2 is going to give me impedance, I can rewrite that whole thing as this. Okay. Now, this is equation 9.8 derived. And I'd like for you to kind of understand, you know, that process of how we got here. But at the end of this, I want you to see that what this says is the impedance seen by the source, right, we defined here, is really just the turns ratio times the actual value of the load that is connected to the secondary, okay? So the impedance seen by the primary is the turns ratio squared times the actual impedance across the secondary terminals. Now that, just for, you know, a second, is a pretty cool thing to think about. And I can use this in circuit design and other applications to get certain outputs that I couldn't get otherwise. And so he goes on to say that this transformation is real. It's not some you know, illusion or you know, just a sleight of hand there. It's a real thing. And an ideal transformer can modify the value of any component, be it a resistor, capacitor, or inductor. For example, he says in the text, I could have a 1,000 ohm resistor placed across the secondary of a transformer that has a turns ratio of 1/5. And that turns ratio I could square, okay, and multiply that value by whatever the load was. So let's do that. Let's see what that would do. What is that looking like? So 0.2, and I'm going to square that with my calculator, and I'm going to get this 0.04. So if I say 0.04 times, say in this case, a load of 1,000, right? So that would be 1, 2. So I would end up with a value of 40 ohms. So what does that mean? Well, what that means is the source would see that load at the secondary not as a 1,000 ohm resistor, but as a 40 ohm resistor, okay? Don't overthink it. Don't try to take that to any place else right now. Just recognize that that's the case. It could also do the same thing for a capacitor that has a reactance of 40 ohms, or an inductor that had, you know, I meant to say 1,000 ohms here. I'm sorry. I'm not. So if I had a capacitor hung out here at 1,000, or an inductor at 1,000, inductive and capacitive reactance to the source, both of those would appear as 40 ohms. Okay. Now we'll follow this through later, and we'll see some interesting things that we can do with that. And then the last thing he says there, you know, talking about, say, the 1,000 ohm capacitive reactant capacitor because the reactance of a capacitor is inversely proportional to the capacitance, and you know, I don't know, you know, sometimes maybe it helps to relook at some of these old things that we did. The inverse relationship between that and the capacitance, right? So, you know, this number gets smaller and smaller and smaller, right? The other gets bigger, but that inverse relationship across there, he said the apparent capacitor between the primary terminals is 25 greater than the actual value. But, you know, anyway, that's just, you know, just a specific example, you know, dealing with the particulars of how this capacitive reactance is developed. He said we could therefore artificially increase or decrease the microfarad value of a capacitor by means of a transformer. Okay, well, now we're going to come up with some ideas why we might actually want to do that. But the main thing I want you to take away right now is this, that the impedance, apparent impedance seen by the source in an ideal transformer is equal to the turns ratio, or the ratio of transformation squared, times the actual impedance that is connected to the secondary terminals. Okay? And I'll stop at that.